In my videos, I tend to flip through a lot of different weather maps, and I'd like to just take a step back and look at what they all are. So welcome to another video. It's not a typical forecast, but we're going to just be checking out the different levels of the atmosphere, looking at the different maps, and so people can really understand what I look at and what I use. Here is our 500 millibar map. Really though, I have a lot of different weather models, and I'd like to explain this whole home page. So up on this top bar here, you can see we have a lot of different weather models I can use. Ones I'm typically using are going to be the rapid NAM models because they're more of a synoptic scale pattern kind of model. So they are convectively allowing, which means they will go through precipitation, thunderstorms, and they will affect how the model goes. However, for the most part, these ones tend to stay independent of thunderstorms, so they're more useful to understand the broad overview of an environment. The more convectively allowing models I use are going to be the HRRR and the NAM Nest model here. So these two both will do a lot more high resolution reflectivities, such as thunderstorms and other sorts of precipitation events. They can be more useful for looking at the specifics of a certain event, for example, severe weather. I'm going to be using, for example, this event here. I believe that the NAM Nest will take us out this far. You can see how much more well-defined all this reflectivity is compared to the RAP model, who kind of makes it look a lot messier, and this isn't normally what you'd see on a radar. You see something more like this. That's the general overview of that. Let's go back here, though. I'd also like to show you guys, just from the broad overview standpoint here, what the map usually is. So you can see I have my big map here, which is almost always going to be the 48 here, on parts of Canada, parts of Mexico. But usually when I'm at any map, such as a 500 millibar map here, you can see on the they're underlined out underneath the map here. Here's Illinois, here's Texas, and they can be hard to see sometimes. So if you're confused on where I'm looking, usually it's going to be underneath here. So you can see all the little lines in there, again, a little bit difficult to see. There are some other maps out there that do this better, but just because I know this website more, this is what I use. And the other models up here we also use are the GFS. Sometimes we use the European model here. And I like to use this ensemble forecast for more long range things. This is just a bunch of models put together. Here's ensemble winds. This map is going to be spread out over 20 different models you're going to see on screen now. You can see all these different models and how they resolve the environment. What the ensemble does is it actually combines all these and basically takes, average kind of thing and sees what it can see. So you can see on these models here, so this one, this one, this one, this one, let me a whole bunch of these. They have this little cutoff low down there, if you can see it. It's a little difficult to see. So you have this little cutoff low kind of off the Pacific coastline in the US. However, other models like this don't really show it very prevalently at all. Other models show it way over more to the west, other models over to the east, and that's where you kind of get that divide. So you can see on the mean wind how this is very well defined and the models agree on this, but they only somewhat agree on this cutoff low and where it will be. Again, if you see this model, this output as well, this is our spaghetti plot. This is basically all of the different models and certain geopotential heights, which is a 500 millibar thing that I'll show you how they're agreeing. So you can see how, for the most part, here they're mostly aligning, and these green ones here are also fairly aligned as well. However, over time, they just kind of become a mess. Right at the end of the period where they're going to have the most variability, you can see it's just a mess of lines everywhere. But actually, for this specific instance, they're agreeing for quite a long time, actually. And you can see the general consensus here is troughing over this region. So that's interesting. So yeah, there's all the weather models up there. And what I'm going to do now is just go to the NAM. We're going to go through all of these ones in the left side panel. You can see this left side panel here as well. I have a lot of different options I'll use sometimes. I can change the time of my model. For example, I was actually outdated there, but I moved to the most recent run. You can see all these different models here. I have winter weather, precipitation, convective. There's all sorts of things here I can use. Also, if you're confused on where I am, if you're ever watching a video, you can actually just check up here. Yeah, you'll see where I am. So that's 500 millibar isotax, but that's basically just the normal 500 millibar map. It's the 500 millibar wind speed up here. So you can see again, 500 millibars is up there. If I'm ever looking at surface temperature, you'll see that up there as well. 2 meter temperature, that means 2 meters above ground level. So essentially just what's the temperature going to be at the surface. And you can also see this product has 10 meter winds as well. And overlaid over this is pressure. And we'll go over the surface products in a little bit. But again, if you ever are confused on where you're looking, you can see up here, your time frame is actually going to be on this corner here as well. That is useful for if you're ever watching the videos. So let's go through the list here now. Here's 250 millibars. I rarely use this just because I think it begins to get a little bit clunky. However, 250 millibars is the best level to see our jet stream because that is where it is. If you're ever wondering where there's a jet stream, you can see it very well defined here. It actually becomes a little bit hidden right here at 500 millibars. So the area of strongest flow aloft is actually here. I wouldn't have seen that at 500 millibars. Interesting. So this would look like a more mature trough, but if you look at 250 millibars, it looks less mature here. Again, 250 millibars is better for looking at things like this, and I would like to continue. I'd like to use it more, but 500 millibars is often more easy to look at and more simplistic. 500 millibar wind speed is very similar. This is more wind speeds at the mid level. So this is, you can see on these numbers here, you might wonder what those mean. Here, I'll circle that for you. 5820, what does that mean? So that 5820 contour line is a line that shows where, and everywhere on here, this is going to be a height of 500. So where the pressure is 500 millibars and what height in the atmosphere that is. So that is indicating at 5,820 meters that your pressure level is 500 millibars. Similar thing happens when you see, one right here. This one says 5220. It's the same thing. So what that indicates is that there is lower pressure over here than there would be over here because of the fact that you have that the height of the pressure level is lower, so there's basically less air underneath it, lower pressure. There's less air pressure, less air pushing down over there, so there's less pressure over here. Next, if we look to 500 millibars, we go to vorticity now, and this is going to look a little bit different. It's a little easier to understand when you get a big trough. This is a Sunday event that I'll make a video for soon. You can see here we have a pretty well-defined trough. Talking about these videos, you can see many circles here. We have closed low, we have low on the base of it, so you can see increased wind speeds. I have it over it, and you'll see as well. So 85 knots around, whereas other areas around, 40 knots. In here, it's like nothing. Vorticity is a measure of spin in the atmosphere, and vorticity is a very useful thing for surface low development. Sometimes I will be using this map for vorticity. The other ones you'll see me use sometimes are going to temperature. So sometimes temperature can also, well, when temperature always has an effect, but I like to look at temperature specifically to see if an event is cold core, how cold the air is aloft. You can see over the US right now, as I'm making this video, you have a lot of cold air advecting into the region. Negative 37 degrees Celsius compared to regions over Texas where you get negative 13 degrees Celsius. So very, very big temperature difference there at 500 millibars. You can see right here we have this temperature gradient as well. So when we have this closed low, you can see that regions inside of it are much colder than regions outside of it, even to the north. We have a minimum temperature in here as well, which is associated with low pressure. Low pressure aloft is associated with cold temperatures aloft, whereas the surface is kind of the opposite, actually. Then, yeah, again, you can see temperature gradients are important for weather because the atmosphere likes to be equal, so it will attempt to move more air into the low pressure and the cold setup. That's really about it that I use for 500 millibars. I don't usually look at relative humidity, but this is a measurement of how much air there is in the air. Next thing I will do is look at 700 millibar wind speed, which is very similar. However, 700 millibars is often more useful for finding shortwave troughs. Shortwave troughs are often responsible for severe weather events, so sometimes what they do is cause a very subtle forcing mechanism. So you have a trough that actually helps to indicate lift, and shortwave troughs can help to make very discrete lifting mechanisms. I'm going to see if I can find one here. You might be able to see one here. You can see with the contour lines, they do have a little bit of a kink right there. Somewhat. I'm kind of pulling at straws there, but this can help to find your shortwave troughs. I'm trying to see if there's one out here either. I might say there's a shortwave trough right up here. You can see how they have its little kinks right here. This might be a shortwave. That's not very well defined at 500 millibars. So you might miss that shortwave, but looking at 700 millibars, you can see it a lot more well. That's the main thing I'll use 700 millibars for. You also might use this for relative humidity again. It helps to see what your moisture is at the mid levels. For example, this trough we have moving through a lot of moisture up here in these regions. That will help with snowfall. 850 millibars, again, we can use wind speed. This is often useful for looking at how much supercells will rotate. So when you look at severe weather, 850 millibars is relatively close to the surface. Let me just take a sounding really anywhere. I'm just taking one from Illinois. But you'll be able to see on here where 850 millibars is in a SQT. And frankly, a SQT understanding is honestly something for another video, but you can see on this left side we have pressure, and we have more pressure at the surface, and it decreases exponentially very quickly with height. So from 0 to 1 kilometer, you have almost over 100 millibars of decrease, whereas from 1 to 3 you have, I mean, if you just keep it going up here, 100 millibars of decrease. 200 to 100 is more like 4, maybe 5 kilometers here, compared to the surface where it's a lot faster, or a lot faster decrease. So that is interesting as well. The 850 millibars is right around 1 point, say probably like 1.2 kilometers right there. So very close to the surface, and that can help to rotate your mesocyclones and supercells. That's why I'll look at this model, this output sometimes, because you have stronger flow. For example, there's severe weather associated with this trough that's going to be going on. Again, you're probably watching this video in the future, but there's trough here you can see is having this associated stronger flow, and that might help to rotate some supercells. That is something you might look at, but also temperature advection is very useful. I look at dew point sometimes. Dew point, if you see this green and blue, it's almost always dew point temperatures. Temperature advection is also very useful to look at. And here, warm air advection north of the front as well is going to help with some freezing rain. But if you look at this low pressure here, this is at 850 millibars, but it is also associated with a surface low here, and we'll talk about that in a second. But temperature advection, there's warm air advection here, and lots of cold air advection here. So regions here are going to get colder very fast. That's another reason I look at 850 millibars sometimes. Other models I don't tend to use very often. I also don't tend to look at 925 millibars, just because it's very similar to 850 millibars and would be kind of redundant. But it is useful as well, and any of these things are going to be useful for forecasters. But each forecaster has their own models they like to use, and I personally don't tend to look at 925 or the 250 very often. Next, the most important part sometimes is going to be the surface. So here is surface temperature. So we can see temperature by colors, and you can expect that these cooler colors are going to be colder temperatures, and the reds and the oranges are going to be warmer temperatures, which makes sense. But on top of that, we also have pressure lines, so we can see these is just what the pressure is at the surface. Lower pressure in this little bullseye. You go north up here. This is an area of high pressure. Just a reminder that high pressure in the northern hemisphere, which is where all my forecasts thus far have been, high pressure is a clockwise rotation, and from high pressure you actually go outwards a little bit. You get divergence from high pressure, so that's important. And it's a similar story for low pressure, but just the exact opposite. You actually get counterclockwise rotation, and you get convergence. So winds will actually go towards the area of lower pressure. And that is why we see thunderstorms and rain with low pressure, because you get that convergence, and that can help to fuel your precipitation. So here's our temperature map. I'm actually going to zoom in down here just so you can see a little better what's going on. So you can see we talked about the pressure lines, but we have temperature, which can indicate, frontal boundaries. So you can see we have this shift from colder air to warmer air, and also associated with some wind movement. So here we have a wind vector, circle a little better. There's a wind vector mostly from the west, and then there's a wind vector from a little more of the south. That might lead me to place a cold front right around here, because you have that wind shift and you have that temperature shift. I also, for placing frontal boundaries, might look at theta E, up to show where your frontal boundaries are a little better. But theta E is often a measurement of, like, more so instability kind of thing. I'm a little bit foreign on the concept, but it can be useful for checking out areas of different air masses. So you can see a lot colder air here. It's very similar to the temperature look, but just a little bit different. You can place your frontal boundaries a lot easier. You can see our temperature gradient is not really strong here. Compared to theta E, you can really see that boundary right there. Similarly for the warmer front right there as well. And that little bit of occlusion, you can see it a little better here by looking at theta E. Dew point can also be very useful for placing frontal boundaries. You can see, again, very well defined frontal boundary right there, and yet another one right there. Dew point is a measurement of how much moisture is in the air. So essentially what dew point is the temperature at which condensation occurs. So if you have a 12-degree dew point up here, kind of near Lubbock here, 12-degree dew point is going to be, once you hit 12 degrees Fahrenheit in temperature, that's when you would get clouds. So also, dew point is also a measurement of how much content, like how much water vapor content there is in the air. So if you don't have a high dew point, there's not much moisture to work with. Actually, this is a case of winter weather. A lot of the time, you have relative humidities of near 100%. Of higher relative humidities away from warmer temperatures. For example, see regions in Kansas here are very, very cold because there's. I'll zoom in here. Here's Kansas and Nebraska. If you look at relative humidity, you would think it's very moist here. And that is true, and most likely that actually it would be snowing there. But temperatures are very low, and dew points are also very low. So that's the reason why the relative humidity is higher. Not because of the fact that there's more moisture, it's just the fact that there is the amount of moisture in the air is basically at maximum compared to regions out here, maybe in, I don't know, central Texas here, where the relative humidity is very low. There's actually more water in this station than there is up here, even though the relative humidity here is significantly less than up here. Dew point is a very good measurement, though, again, of moisture. And you can see here, if we look close to the ocean here, high dew points because there's just so much water over the ocean. And when that affects over land, you can see you get more moisture, more thunderstorms. Like, for example, this is a thunderstorm setup here. You have that front, and you have that dew point gradient, the moisture gradient. That's important as well for severe weather, especially when you're looking at dry line. Yeah, so I talked about temperature, dew point, and theta E. Again, if you're ever confused on what I'm looking at, this is a very good spot to go. Typically, if I'm at the surface, I'll be looking at temperature, sometimes dew point, and you'll know when it's dew point because of this very clear blue and green thing you'll see here. Also, all these other lines are called lifted index, and when you see red, that often indicates instability. Now we're going to look at convective things. This is almost always going to be used for severe weather. I don't think I ever used this for anything else, but this is called, this is the CAPE map. So this is convective available potential energy. Again, it's CAPE, so it's convective available potential energy. Potential energy is how much lift you might have in a spot. For right here, we have some CAPE going on. SIN is convective inhibition, so it's basically anti-CAPE. How much stability do you have going on? So if we look at this setup here, if I go back a few frames, you'll see this. This is indicating there's CAPE, but there's also inhibition, which is stopping convection. That means that there's some stability left before storms can really get going. And you'll see this again a lot more well-defined in summer setups and stuff. This is kind of, again, we're grasping at straws a little bit because this is a wintertime setup we're looking at, but it still remains the same. Convective inhibition will stop storms. Convective available potential energy, or CAPE, will make storms happen. They're both measured in joules per kilogram. And joules per kilogram, that is just the measurement. Joules are a way of measuring energy. You might hear that in the electrical fields or something like that. Kilograms is just a measurement of how much air there is in a region. So if there's lots of energy per area of air, then you'll get more available potential energy, you'll get more lifting. So you can see on these maps here, you'll often see the states very well, and you can see 10 millibar winds, or sorry, 10 meter winds. That is your winds at the surface. I would place a low pressure right here. Let me draw that in red because it's wrong to do in blue. Low pressure here, probably a cold front. That should be in blue. Cold front somewhere right here we talked about. And you have in that open warm sector is what this is called, have instability. So very, very indicative of a normal surface low thunderstorm kind of setup there. You have this instability. I'll look at different types of instability, but they all basically mean the same thing. Most unstable will not have inhibition, however, and you'll have some different wind vectors that will go on. These wind vectors are actually storm motion. These ones are the surface map, and these are bulk shear. So they're all different in their own regards. Also, sometimes I'll look at supercell composite. This is just a parameter that people have made that kind of says what parts make supercells, what's our bulk shear, what's our instability, that kind of thing. They give you a number on how likely it would be that supercells form. That's not the most important part of forecasts. A very similar thing for STP, which is significant tornado parameter. Sometimes I'll gloss through both of these very quickly just so you can see with colors where you're going to be looking for, where will supercells form, where will tornadoes form, that kind of. Lapse rates are also important. So again, these are all kind of, it really depends on when I use these based on the setup, but I'm just going to go through most of them. Mid-level lapse rate is how quickly temperature changes with height. with severe weather, the gist is that stronger lapse rates mean more instability, because if you have temperature decreasing with height more quickly, a parcel will have more instability and more, the difference in temperature will be more. And remember that warmer air is less dense than colder air. So if a parcel stays, an air parcel is just a hypothetical air. If air parcel is warmer than its environment, it's going to rise. So when you have these lapse rates that are very high, that means that the temperature of the environment is changing rapidly. However, sometimes this can be a little bit misleading. You can see on this backside, we actually have a lot of colder air that does not align with the instability. So lapse rates are not always the best thing to look at. But if you have the region you know where thunderstorms are looking good, if you have a coincident lower level lapse rate that's high, so for example, regions here are showing up on here, we're ignoring this part because this is not in our region of favorite development. This might be more indicative for stronger storm development. And lastly, some of the last things we'll look at is going to be these two: moisture flux convergence and mass convergence. I don't usually look at this one, I just look at mass convergence because they're very similar. Mass convergence is just, how much things are pushing together. So where are wind vectors pointing towards each other? If you have wind here and wind here, you'll get some convergence along this boundary. And that's probably where our storms will be developing that. And actually, let me just test that real quick. Look at HRRR model. Look at precipitation. Oh, we're a little removed. Excuse me. You'll see on the NAM, which is another cam, we'll see right where that convergence was, you get that storm development. So this is, again, a simulated reflectivity, which is actually a very good segue, because we're talking about is precipitation. So the only real thing I'll look at here is going to be simulated reflectivity and total precipitation accumulation. Both pretty straightforward. The simulated reflectivity can just show you what a radar product would hypothetically look like. You see here we have that long line of storms right there. That's basically what it's just showing. And total precipitation accumulation is going to be just how much precip falls. I'll look at different time frames. So this is 6 hours. Pretty heavy rainfall in regions here over a 6 hour period. For 24 hours, you can see again pretty heavy rainfall here for 24 hours. Every once in a while, I'll also look at precipitable water, which is how much water in the atmosphere could fall as rain, and how much would that be. So if hypothetically all of the water over this region near the Arklatex fell, it would be 1.6 inches of water. Whereas if hypothetically this region of water for about Lubbock fell, it'd be about a quarter inch. Average cloud cover occasionally I use, but this is not, I don't like this product very much because oftentimes it just shows a broad area of overcast and it's not accurate. Lastly, winter weather, I will look at precipitation type. This cyclone we're looking at is actually a very good example. Here's our surface. It's actually not the surface map, it's thickness, but it's very similar to the surface map. So this is our bars. This is actually the surface map. I was incorrect about that. The red lines and the purple lines here are thickness, which I have not yet learned how to use, but I do know they're important for wind casting. Here you can see precipitation type. Blues are going to be snow. These different colors are more mixed precipitation, with actually freezing rain is probably this one right here. This is going to be freezing rain. And then regions down here are going to be normal rain. This is mostly for wintertime stuff because you can see where that rain snow line happens and where our region of mixed precip is going to. I'll also look at snow accumulations. Usually this is going to be on this color scheme, like the kind of colder colors. You'll see 6 hour accumulation is very useful. See where you'll get really heavy snow. So region of Nebraska seeing over 8 inches in 6 hours is very scary. Or 24 hours, you'll see very heavy snowfall in regions like Kansas right here very quickly. Those are what I use. And lastly, I'll look at freezing rain accumulation sometimes. For this event in particular, there's this risk of freezing rain going on. That's important as well. And some people will use critical thickness. I just have not yet learned what this is. So that's what I'm going for college for. That's all of the products I'll use. I guess snow depth occasionally, but this isn't. If I'm ever using a mysterious product I'm not usually looking at, then I'll tell you guys. So that's all our products for this page. Not much else, but I did want to look at and explain what the SPC products are. This is an SPC Outlook from a little while ago. This is that big old severe weather event. Technically last Saturday, but this is December 28th, 2024. It ended up the year on a pretty significant severe weather event. Lots of tornado reports in there. What this Outlook is actually what it is the chance of any severe weather within 25 miles of a point. They do say this, but oftentimes it kind of gets mislooked, and it can change how you view these. So on here we have our day one tornado outlook. You can see it down here. It's probability of a tornado within 25 miles of a point. The hatched area, which is that the black little lines there, is 10% or greater probability of stronger tornadoes. So that's EF2 to EF5 tornadoes. I believe that's over 110 miles per hour of wind speeds, basically. So very strong tornadoes. What that's showing is that's 10% or greater probability of strong tornadoes in that region. And do remember, these are people making these forecasts, not some computer. This is real hand analysis, and these are some of the best forecasters in the world. So essentially what this map here would mean is this is the tornado map. These also have unique colors oftentimes, but I will be saying that if you're ever just wondering based on the map, you'll see this is the SPC page for convective outlooks. Go to this one here. Up here you'll see categorical, tornado, wind, hail. This one doesn't have an actual outlook. There's just some possible thunderstorms, but when I hover over tornado, you'll see this on red. Wind will be on red, hail will be on red. That'll often change the colors of the map here. See, this is the hail outlook, wind outlook, and tornado outlook here, with that day being tornadoes the main threat. But what this means is that within 25 miles of a point, you have possibilities for severe weather. If you're in this red area, it's not a 15% chance that you will have a tornado. It's a 15% chance that within 25 miles of you, there will be a tornado. So that is important, and that often gets kind of changed. Now, I might actually mislead you guys on accident with that as well. So just do keep that in mind. I'm not trying to say you have a 15% chance of tornado, but any chance of a tornado is something to keep in mind, or severe weather as a whole, because it can always be life threatening. If I chose this point here in Mississippi, again, 5% chance within 25 miles of that point. Same thing here, 15% within 25 miles of that point, and at least a 10% or greater probability of those significant tornadoes there in Mississippi. And same thing for damaging wind. These often have larger percent chances, so and 30%, bigger jumps. So the 15% here would be a slight risk, and the 30% would be an enhanced risk. Compared to up here with the 10% would be an enhanced risk for tornadoes. Down here, this is only a slight risk of hail. This is an enhanced risk of wind and a moderate risk of tornadoes. That's kind of how you read those. If you want more information, you can always check out the SPC page. I highly encourage it. Very useful. And whenever they make their outlooks, they have an explanation of what's going on. So for the 4th, this is when this is. When you have day 2, that means the day after today. So I'm recording this video on January 3rd. Day after today is January 4th, and this is that thunderstorm outlook. You can also see this region here. This is just general thunderstorms, nothing severe. But they have very nice explanations on what you're looking at. That if you ever want more information or want to learn more about thunderstorms, you can always go here. Sometimes we'll have some words that are confusing, and that is perfectly okay. Lots of good information on the SPC page, though. Lastly, I wanted to look at surface map. Again, we looked at that on the models, but the real surface data is always different. Here's some surface data for regions in Illinois. What I want to decode here is just what these mean. So if let's take the O'Hare right here. This is the O'Hare Airport. That's their ASOS station. I have this wind barb here, and if you ever want to learn more about service stations, you can always look that up. But really, the most important things I'll look at is going to be wind speed. So here you have about 15 knots because you have the big flag here, little flag there. We have northwesterly wind because you're coming out of the northwest. Again, remember your cardinal directions here. It's called northwesterly. It's also just called northwest wind because it's coming out of the northwest. I might use those terms interchangeably. Then when looking at this, you'll see the top number here is going to be your temperature. This number is your dew point. Actually make that green just for. So that's your dew point, that's your temperature. And over here you have your pressure. So that's in millibars, and that's actually a little bit differently read as well. So when you have a number between 0, so about right here, to I believe 500, you see that up there. This would be 1,000 millibars versus 10,050 millibars. So kind of have to imagine there's a decimal point here. Numbers before you have to kind of infer. You won't. It's very rare to see 1050 on a map or 950. The same thing goes the other way around. If you see a 987, that's 998.7 millibars. That would indicate lower pressure. not 10,000, not 1,998 millibars. That's going to be 900. That's what I'll look at very quickly. And also these circles, when they're filled in, means cloud cover. You see regions here in, not Orlando, O'Hare, you have about a quarter of the sky covered with clouds, whereas in Valparaiso here, you have full cloud cover. And also on these maps, you'll often see down here, very bottom left corner, that's your date. So this was at 15Z, which was actually an hour and a half ago. So this is outdated data. And almost always data will be somewhat outdated. You can never get perfectly now data. It's very rare. But that's what this map basically means. So hopefully you found this video enjoyable. Again, you have all these different levels of the atmosphere. They're always very different, but all work together in some way. And I do explain what I'm looking at in the videos. I try to do that, but if you're ever lost on what I'm looking at, just always remember you have this top left corner, this top right for timestamps, and you can also just listen to what I'm saying. Captions can also be useful, although sometimes they're a little off. And this is the basis of this video. So I appreciate you guys. If you watched to the end, feedback, or want to have any questions, just let me know. I will answer those. I'm very open to answering questions. So with that, I'll see you all next time. Thanks for watching, and have a great day.